we had a bit of a conversation about this. We talked about a block sliding down a ramp and tried to compare that to what would happen if we placed something that could roll at the top of the ramp. And do you recall I said that there are three possible things that could happen? It could just slide down the ramp, in which case it would be no different than a block sliding down the ramp. But then it could slip down the ramp, which means that its angular speed would be changing, but it wouldn't be rolling. Today, I want to talk about the conditions for rolling. Because before we can do any transitional problems, we have to understand how rolling actually behaves. And I want to be as open and as clear about this, so I'm going to be kind of slow and deliberate. Rolling doesn't behave the same way you might think it does. And that's kind of the reason why I want to be super explicit. Because when we start talking about something rolling up a ramp or rolling down a ramp, you are going to be expected to understand how the forces are impacting the answer. So let's start by just understanding that rolling can only be accomplished if the point in contact has no slipping at all, which means our object is not sliding in any way down the ramp. This point in contact is at rest. So when something rolls, the point that touches the ground is not moving with respect to the ground. This would be true whether this was a ramp or whether the surface was level. But I want to understand how rolling occurs on a ramp, and I want you to understand it too. Now, we've talked about the three forces that are acting on an object as it slides down a ramp. Those forces aren't any different now that we're talking about an object that would roll down a ramp. In fact, let's talk about those three forces. There are three forces that will act on an object like this. And I'm going to draw them super big so that we can kind of see them very clearly. First one is the one that I would say is the easiest because it's the one that you guys know. It's gravity. But you'll notice I'm drawing gravity at the point where it acts on the object, the center. Nice and big. Now, there's also a normal force. The normal force has to be drawn so that it starts at the point of contact and is perpendicular to the surface. The very first thing I want to point out about the normal force is that the normal force can't cause a torque. Look at the direction. It points through the center of the object. So it's difficult for it to cause a torque. Now, friction's tougher. To understand the direction of friction, you have to know ahead of time which direction you think this object is rolling. So we have to know whether we're talking about something that's rolling up the ramp or something that's rolling down the ramp. I'm not trying to make it hard. Let's start with the idea that this object is rolling down the ramp. Now still, how do you draw which direction friction acts? I think most of you are probably going to get it right, even if you're just guessing. But the direction of friction has to be to cause the wheel to change the velocity the right way. Is the wheel going to be spinning faster as it goes down the ramp or slower as it goes down the ramp? So the only way to do that would be if something were to push on its edge in this direction. Now, here's the truth of how this is supposed to work. And when I say the truth, what I mean is a lot of people believe that when we analyze the forces here, we should analyze them as if the pivot point is about the center of the object. And if you do that, you will get the correct values for everything. So it'll work. So you can do an entire problem from the standpoint of the middle. But if you really want to understand the physics, you have to note that the actual pivot point is this. An object that rolls pivots about the point in contact because that's the point at rest. The center of the object's actually moving and isn't the true pivot. Now, the math works out regardless of which of these two things you choose to use. So it won't make any difference. But the true pivot point for an object that rolls is the point of contact. Now, that being said, I want you to understand what it is that doing this is about. The only reason you will do this is if you are asked to find the size of the frictional force. It is the only reason to do the force problem for something that's rolling. In any other circumstance, energy will be faster, more deliberate, and will allow you to calculate anything else. Acceleration, velocities, all of that. So the only time you would have to do this, I think, is if you have to find the force, the frictional force. Well, we're going to work this out, but this is tough. Now, I want you to understand a few things here. First, net force does not go away just because our object is rolling. The force down the ramp minus the frictional force is still what drives the acceleration of this system. Meaning, I'm not going to break this into the components. We've done that a dozen times. In the x direction, which is the direction down the ramp, that's the direction it's going to be accelerating. In the y direction, the net force is going to be 0 still. So all the things from a box sliding down a ramp still apply here. So mg sine theta, where theta is the angle of the ramp, minus the frictional force equals ma. That's still true for an object that's rolling. And moreover, the normal force minus mg cosine theta has to equal 0. That still is true even though the object's rolling. What's very unlikely to be true is that the static friction will equal mu times the normal force. That is very unlikely. It usually only requires a very small amount of friction for an object to roll. So usually this is not just less, but much less than the maximum force. Most things will have enough friction. Even snowy roads and icy roads often have enough friction for things to roll. So it's very unlikely you'll ever have those things be equal. The frictional force is much less, which makes this almost always useless in trying to figure out the frictional force. So you have to look at torque. Net torque is going to equal I alpha. There is an unbalanced torque acting on our system. And here's where pivot point matters. If you do this problem from the standpoint of the center of mass, then the torque comes from friction. So we're going to split this. We're going to do both problems. We're going to do it center of mass, and we're going to do it again, point of contact. Because it only takes a second to do both of them. Net force from center of mass. If we're doing it from the point of the center of mass, then this has got to be our torque arm. So that's what we use for our torque arm. In that case, it's going to be RF sine 90 degrees. Also, that's going to equal I center of mass times alpha. Right. The point of contact is harder. So let's do the point of contact. When you're dealing with the point of contact, do you realize that the frictional force is at the point of contact, so it does not provide a torque? Same reason why I didn't bring up the weight, because the weight was acting at the center of mass. If that's my pivot point, it doesn't provide a torque. But in this case, the only force that's actually causing a torque, if this is my pivot point, is going to be the weight. It acts a distance r away from the pivot point, The size of the force is mg, and in this case, it's sine theta. It acts at this angle, which is the same as the angle of the incline. And now it gets worse. This equals I parallel times alpha, right? If we're going to deal with the point on the edge, then we have to use the parallel axis theorem. All right, here's the thing. Friction is an unknown. We don't know the size of friction. The only way to find it is to eliminate the acceleration. There's a case to be built that it's easier to do that here than it is to do that here. The reason is because you can find the acceleration right here. I can get a value for the acceleration. Everything in this expression is known. This has both unknowns in it, and this has both unknowns in it. All right. Well.